Okay, so we should be recording. And welcome to CSC 475. Today what we're going to be doing is we're going to be talking about some search strategies. But before we do that, I'd like to ask whether there are any questions about the programming. Notice that some of you do not have your volume muted. You might check to make sure your volume is muted.
Yeah, that was me, my bad. I was having audio issues. Not that you can.
So do we have any questions about the programming assignment? Anybody? Okay, so the programming assignment is due Thursday, 2 days at 9 o'clock in the morning. It has to be in by 9 a.m. And basically you need to email me your programming assignment before 9 a.m. Please check the assignment. The details are in there about what the subject on the assignment is to be. And it's got my email address, which is mike@lawtech.edu. Also, too, if you go and you look on Moodle now, under assignments, there is a resource called Assignment 2 Code Review Sessions. I see that about 14 or 15 of you have discovered this already, but that link will take you to a Google spreadsheet, and in that Google spreadsheet you can put in your time that you would like to meet. So, for example, here's what the sheet looks like. And you can see that on Thursday and Friday we have slots that you can fill in. Like I said, some of you have already done so. If you haven't signed up already, please go ahead and sign up. Note that the spreadsheet is does not have race condition protection on it. So when you sign up, I would suggest that you check the spreadsheet a few minutes after you signed up to make sure that that you really do have that slot. If two people are editing the slot at the same time, there could be an overwrite condition. So just so you know that. At the same time, do not go in and change a slot that already has somebody else's name in it. There's a history feature, so you can see who's editing the slot. Like Noah's looking at 11:45 to 12 right now, and if a slot gets changed, there's an edit function, there's a history function. So don't go and change someone else's name, because it'll be apparent that you did that. But like I said, if two people are innocently editing a cell at the same time, there can be an overwrite condition, because there's no locking on the individual cells in Google Docs. It should work out fairly well, I guess. If there is absolutely no time that's available that you can make, you can email me. I would be very reluctant to put on any times outside of the times that I've assigned here, because it becomes a giant pain if I've got people who want to meet outside of these times. At the same time, if you work on Fridays and in Monroe, and it be a big, hassle on you to try to get over to do well, you don't have to come over because we're doing these online, but if it would just be totally impossible for you to do one of these online, send me an email and we can talk. But I would strongly, strongly prefer that people sign up on the times that are available. Okay, are there any other questions about programming assignment? Again, are there any questions? Everybody sees the sign-up sheet now. You'll see that there are 15-minute slots. We'll do these over Skype. If we lose video, I'll be signed in by my phone, since everybody will have sent me their programming assignments by 9 a.m. on Thursday. It would be more difficult, but we can still go through and do your walkthrough, even if we only have audio, as long as I've got a copy of your program that I can look at, and you can look at it too, and we can talk about it. Any questions about the meetings? Again, look at the programming assignment handout. I've had a number of people ask me about, partial credit and stuff like that, and how it's scored. There's a rubric on the back of the assignment that shows exactly what happens. One person was asking about, well, do I have to get the visualization working to be able to get partial credit? No. The visualization part is actually for bonus points. It's for 10 extra points. So if you didn't do quite as well on your midterm or your term paper, or you're afraid that you might not do as well on the final exam, there is an opportunity for you to be able to earn 10 extra points on the programming assignment, an extra 10%. It's pretty easy to get that. Like I said, the ASCII art should be the one of the least difficult things to do. Okay, so that's the programming assignment. Final time, any questions about the programming assignment? Okay. I'll be in my office hours tomorrow, only about 10:30. That'll be the last office hours before it's due. So if you've got questions, that's the time to come in. A number of you have done that, so that's good. I wanted to also take a very few minutes and talk about the exam. Everyone should have received their grade on the exam. I wrote an email for an individual email to each of you showing the points that were taken off. Also, there's a key with answers that's been posted, so you can check that against your little email to see where you went wrong. I tried to write in many cases I wrote a little comment about why something was wrong, but if you want to see the actual answers and the calculations, they're on Moodle in the exam section where I posted the entire thing. But in the end, the grades turned out better than I was afraid they would when we last talked on Thursday. You'll remember, I think on Thursday I'd only had like 1 A, or maybe I just graded the second A. It ended up that we had 8 A's. We had 13 B's. There were 40 people altogether. This class started with 43 people, but 3 of them dropped out before the final, before the midterm, so that gave us 40. So you can see that over half of you made either an A or a B. The median grade, that's the grade in the middle, was a 75.3. The average of all of the grades was 75.3. The median grade was an 81. So it's skewed a little bit towards the top end. It's not quite a normal distribution. And then you can see that they went on from there. there were more low grades than I like to see. And again, the median was a 75. Sorry, the median was an 81, and the mean was a 75. But and it makes sense that the median was an 81 since over half the class made an A or B. If you are, if you're in the 30s or 40s, you should probably drop the class. If you're in the 50s, it depends, right, on what kind of grade, you expect to make in the class. Yeah, how good a programmer you are. If you're a pretty good programmer and you made in the 50s, you might want to stick with it. But, these are the grades. The standard question always is, Mike, do you ever curve? I do sometimes apply a small curve at the end of the quarter. I won't know whether or not I'll do that, and I won't know the size of it until I have all the grades turned in. So do not depend on a curve, but know that if you've got an 89, that's probably going to end up being an A, right? May not, maybe a B. That's what you're guaranteed to get what you earn, but if you're close, and what I really do, I look for. What I do is I look for breaks in the grades. So let's say that you have an 89, okay? If the next highest grade was a 94, then you're probably getting a B because there's a huge gap between that 89 and the lowest real A of a 94. But if the grades, are like, I've got some A's, and then I've got like a 93, a 91, 2 90s, a couple of 89s, and maybe an 88, and then the next grade's an 86. Well, those 89s will probably move up, and maybe even the 88 might move. So that's kind of the way that works. Okay. Any other questions? Cody, you missed the most important thing. That is the video intro from Silent Running, and an explanation of the background here with Huey and Dewey, or maybe that's Huey and Louie. There were 3 of them, Huey, Dewey, and Louie, little box, in the movie Silent Running. So check out Silent Running if you want to watch a hippie eco movie from the 1970s that's set in space. Okay. Any other questions? Okay. So what are we going to do today? Today we're leaving machine learning behind, and we're moving into good old-fashioned AI, and we're going to begin that by talking about gameplay, state spaces, and search strategies. Now you might say, okay, I can tune out to all of this because you said it's good old-fashioned AI and nobody uses that anymore. Tisk, tisk, tisk. These ideas are used in some of the most cutting-edge computer machine learning programs to this day. If you look at AlphaGo, AlphaGo Zero, AlphaZero, and the newest one, U0, they all use tree search to a certain degree. So these techniques are still very widely used, and they're used in, as I said, in some of the most cutting-edge programs. So it's not something that you can say, oh, that's old. We don't have to worry about that anymore. So anyway, let me see. Here. One second. So let me share my screen here. Here's a tree, and you can see actually that this is a graph rather than a tree. I mean, it's got a root at the top of A, and then A's got 3 children, B, C, D, and B's got 2 children, E and F. But F has a child of A. So this isn't a tree, it's a graph because it has nodes that can connect back up the tree to ancestors. And also, if you look at D, D has 2 parents. It has A, and it also has C as a parent. So there are 2 paths that you can get to D from. You can go directly from A to D, or you can go from A to C to D. In this little graph, you see that certain nodes are marked as red nodes. E, H, and K are red. Those are failure states. And 2 nodes are marked in green with a double circle around them, M and L. Those are goal states. So one of the first things that we're going to do if we want to use search in AI is you have this concept of these search spaces, state spaces. They're ways of representing a program. And you might look at this and say, or representing a game, you might look at this and say, I've got no idea, Mike, how this thing might represent a game. But think for a moment of a maze, a single player game. You've got one person playing the game. And the person's trying to get from the entry point A to an exit. And then this one, you happen to have 2 exits, one labeled M and one labeled L. And you could think of the arrows as sort of branch points. You know, I can go left, I can go straight ahead, or I can go right. So in that sense, the little circles represent positions in the maze, and the arrows represent, you know, directions you can next move in, walk straight 1 step or 10 steps, whatever it is. You know, walk right 10 steps, walk left 10 steps. And so you can think about the idea of exploring a maze as a search space. Now, in general, you're not going to know when you begin what that entire search space is, right? Think about it. If I'm standing at the beginning of a maze, all right, I can only see like what's right in front of me, so I don't see the whole state space. That's okay. We generally discover the state space as we move along. If you think about doing a search through a space, you don't always know the whole graph first. All right. Now, what are some ways that you guys have learned to search through a space? Well, all of us have had 325. So, and in 325, and probably even back in 220, you would have talked about depth first search and breadth first search. Those are the 2, like, you know, first search algorithms for trees or graphs that you learn about. And basically, we in AI refer to these searches as blind searches. Depth first search and breadth first search, we refer to them as blind searches. And the reason why we call them blind searches is well, you don't really have any way of seeing what's up ahead. It's like you can sort of feel what's directly in front of you, right? But that's about it. And so the searches are blind. So just to review, how would depth first search work on this graph? Well, in depth first search, you look at, is there a question? If you don't have a question, would you please mute your mic because we're hearing your background. Okay? All right, thank you. So in depth first search, what would happen? Well, depth first search, you look at your children before you look at siblings. So in depth first search, you would start at A at the root, and you would feel out or touch or open your children, B, C, and D. Okay, so you've touched your children. You haven't explored them yet, but you've touched them. You know that they're there. So then with depth first search, you would go after your first child. Now, traditionally, when we draw it, we go from left to right. That you do. Nothing in the search says that you have to do that, but generally you go from left to right. So you open up A, you see that you have children B, C, and D. You then explore the first child. So essentially you go from A to B. Okay. And then you explore B's children, you open them up and you see that they're E and F. Okay, so now then you have open nodes E, F, C, and D. And you take B's first child, which is E, and you go there. So now our path is A, B, E. But when you get to E, it's marked in red. It's a failure state. It's like you hit a dead end in the maze. So you back up to B, all right, and now you go to B's next child. So you see that B's next child is F. And so now then you go, the path becomes A, B, F. Okay, so I lost my background. I don't know why I lost my background. Gotta have my background back. I'll use a different silent running background. This one's got a pretty picture of Saturn in the background. So we went from A to B, from B to E. We had to back up and go back to B. So now we're at A, B, and we go to B's next child, which is F. And so now our path is A, B, F. And what are our open nodes? Well, we look at F's children. F only has one child, A. Okay. So now our total open nodes are A, C, D. And we open up A. And we find that A has children B, C, D. And so we go to A's first child, which is B. And then we look at B's two children, and we go to its first one, which is E. It's a dead end. We back up to B. And then we go to B's next child, which is F. We open it up. It has one child. We go to A. And you see what's happening here. We're stuck in an A, B, F, A, B, F, A, B, F, infinite loop. So one of the disadvantages of depth first search is that it can get caught in an infinite loop. If your search space is a graph, which allows you to revisit nodes that have already been visited before, you can get into these kind of loops. Now, it's pretty easy to add loop detection to depth first search. So basically what you do is every time you add you're about to open a new node, you check and see, okay, so I went from A to B, I went from B to E, I backed up because E was a failure, and then I went to F, and then I opened up and I saw A. Well, before going to A, before going to any node, you ask yourself, is this node that I'm about to go to already on my path back to the root? And so in this case, A is, because the path so far is A, B, F. And if you find a node that's in that path, then you just clip it. You cut the little link here and treat F as a failure, because it is a failure. F, if you explore past F, you will go into an infinite loop. That's just as much a failure as running into a dead end. This represents kind of running around in circles in the maze, right? And you can do that forever, and maybe you feel like you're making progress, but you're not. You're just running around in a circle. So let's say that we had depth first search implemented with loop detection. So in this case, A opened B, C, D. You took your first child to B. B opened to E and F, so now you have E, F, C, D. You take B's first child, E, okay? That's a dead end, so you back up to B, take B's next child, that's an F, okay? You open up and you see there's an A there. Well, A's already on the path. If you trace back up, F, B, A, A's already there, so I don't need to open it, so I count F as a failure. So I back up to B. I've got no more children of B because I've explored both of them. So I back up to A, and at this point, C and D are the children, so I would take C. Okay, continuing on, C has two children, G and D. You know, D is actually now in our list of open nodes twice, because you could get to D from A to D, or you could get to D from C. That's fine. So again, after exploring this path and getting back here, we explored C. C had two children, G and D. We take C's leftmost child, which is G. We open up its children. There's only one J. We take that. We open up its children. There's M. We take that. And we have found our goal. A, C, G, J, M. Depth first search, if you implement loop detection, is guaranteed to find a path to a goal if such a path exists. So that's a good thing about depth first search. If you implement loop detection, then if there's a path from the starting point to an ending point, it will find one of those paths, okay? Now, there could be multiple paths. As we see here, you could go A, C, G, J, M, or you could go A, C, D, I, L, or you could go A, D, I, L. Now, A, D, I, L is the shortest path from the starting state to a goal. Depth first search doesn't find the shortest path. It finds a path, but not necessarily the optimal path if what you're trying to do is take the shortest path. Okay? So, depth first search is good if you implement loop detection. If you don't implement loop detection, depth first search can get stuck in an infinite loop. But if you implement loop detection in pruning, then depth first search will find a path. So that's one good thing about depth first search. If there's a path and you've implemented loop detection, it will find it. Okay. Now, depth first search has another really, really good characteristic, and that is that the memory that it uses is linear in the length of the path you're exploring. So you only really have to keep up with a list of the nodes that you've touched, the open nodes, and the path so far. So, like earlier, you know, we went A, B, E, and then we backed up and we went F. But when we get back to A, because this is a dead end and this is a loop, you no longer have to remember the details of what's happening over here as you explore here. You basically, at any point in time, you just remember the path from where you happen to be. Let's say I'm at J, back up to the source node, and you also have a list of nodes that you've touched but haven't explored yet. So a huge advantage of depth first search is that it uses an amount of memory that increases linearly in the length of your path. What are the disadvantages of depth first search? Well, if you don't implement loop detection and pruning, it can get stuck in an infinite loop. Even if you implement loop detection, depth first search, while it is guaranteed to find a solution path if one exists, as long as you've implemented loop detection, it's not guaranteed to find the shortest path. Okay? So that's a disadvantage. It won't find the shortest path. Or it could, but it's not guaranteed to find the shortest path. Okay. A lot of times people think about depth first search as a stack-based search, using sort of a LIFO, a last in, first out. And often we implement this search recursively, right? Where you take a node, you generate a list of its children, and then you recursively call the algorithm on the first child. And you use, recursion to drive the search process. You can implement it manually and implement your own stack rather than using the program stack, the programming language stack, the execution stack. You can do it that way as well. Okay. Is there a search algorithm that overcomes the negatives associated with, excuse me, I apologize. Let me see if I can get this cough to stop. Is there a search that we could use that overcomes the disadvantages of depth first search? And the answer is yes. The next standard search that you learned about in 325 or maybe in 220 was breadth first search. If depth first search is a stack-based LIFO search, then breadth first search is a FIFO, a first in, first out, queue-based search, right, rather than a stack-based search. So in breadth first search, what you do is you start at the source node and you expand. You don't just touch all of the children, you actually expand them out. So from A, I expand out B, and then I expand out C, and then I expand out D. Breadth first search is called breadth, right, with, because it's exploring all of the paths in parallel. That's what it's doing, okay? So again, A, I open up B, C, and D. So I'm really keeping up with the path from A to B, and the path from A to C, and the path from A to D. And then I take the first one and I open it up. So now I'm keeping up with the path from A to B to E, and A to B to F, and A to C, and A to D. Well, the path from A to B to E, E has no children, and it's a dead node, so I'm not going to go any further. It doesn't matter whether or not I have implemented loop detection, as we'll see in a minute. So anyway, I opened up A and got A to B, A to C, A to D, and then I opened up B to E and B to F. So now my paths are A, B, E, A, B, F, A, C, and A, D. Well, I've explored B's children, so now I have to explore C's children. So now I generate ACG and ACD. So now my paths are A, B, E, A, B, F, A, C, G, A, C, D, A, D. And now I got to explore D, right? Frequently what happens when you get something like ACD is you go, oh, I'm hitting a node that I've already seen before. Is the path that I just used to get to this node shorter than the one that I already knew about? And in this case, this is a two-step path, and I already had a one-step path, so I would just essentially generally ignore that link here, because it's just a longer way of getting to a place that you already have a shorter path to. Then I explore D, so that gives me ADH and ADI. And then, so now that I've explored everything at sort of the first level and the second level, so I've got paths that are 2 levels long, ABE, ABF, ACG, ACD, ADH, ADI. And then I go through and I expand each of those to make paths of length 3, because I've gotten all the paths of length 2. E doesn't go anywhere, F goes to A. If you had loop detection, fine, you could do it, but not implementing loop detection won't kill you, it'll just use more resources. So now A, B, F, A is a path, okay? I've got to explore G's children. There's only one J, so I've got A to C, C to G, G to J, And I got to explore, let's see, H has no children, I has 2 children, K and L. And at this point, I have found a goal, okay? And I'm guaranteed, because I'm expanding things a level at a time, I have found the shortest path to this goal. It's a path that has 3 steps in it: A to D, D to I, and I to L. So what's the advantage of breadth first search? The advantage is that it's guaranteed to find the shortest path to a goal. So not only depth first search, if you implemented loop detection, was guaranteed to find a path to a goal, breadth first search is guaranteed to find, if there is a goal, not only guaranteed to find the goal, but to find the shortest path to a goal. Okay, so breadth first search is better than depth first search in that it not only is it going to find a path to a goal, it's going to find the shortest path to a goal. And breadth first search will work whether you implement loop detection or not. In depth first search, you have to implement loop detection or you can get caught in an endless loop. In breadth first search, it's more efficient if you get rid of loop detection, and it's more efficient if you get rid of additional paths to nodes you've already visited. But not doing those things isn't going to ruin the algorithm, okay? You would still, because you're expanding a level at a time, you would still find the shortest path to the goal. So if breadth first search is better than depth first search, why do we even cover depth first search anymore? Why don't we just always use breadth first search and call it a day? Well, depth first search, as I said, only used a linear amount of memory in terms of the length of the path that you're exploring. Breadth first search uses an exponentially growing amount of memory in terms of the depth that you've searched. So while breadth first search would be nice to have, and if you've got a very small graph like this one, is good because it'll find the shortest path, it is generally avoided because it uses an exponentially growing amount of memory. And so for problems of any reasonable size, you cannot afford to use breadth first search. Okay, so that's a summary of breadth first versus depth first search, and sort of their advantages and disadvantages. They do share a disadvantage that I have written up here. The shared disadvantages, both breadth first and depth first search suffer from exponentially increasing execution time in terms of the length of the search path. So breadth first search doesn't use an exponentially growing amount of memory like breadth first search does, but they both will take an exponentially increasing amount of execution time in terms of the length of the search path. So while depth first is better than breadth first, in reality, most of the time, neither of these can be used for problems of reasonable size. Now, one of the problems that we had on the exam said something like, was talking about the early successes that we had in AI. And the problem said something about strong general methods. Well, actually, it was false because it's weak general methods. The early successes in AI were based on weak general methods. Search, depth first and breadth first, but mainly depth first, is an example of a weak general method. It's a general method. You can apply it to any problem, pretty much any single player game that can be modeled with the state space. You can use depth first search for it, but it's got to be a pretty small problem like tic-tac-toe or something for you to be able to explore all the paths. Tic-tac-toe is a bad example because it's a 2-player game. Maze, it's got to be a pretty small maze for you to be able to use the search on it. But like I said, it was a search of a search space is a weak general method. Now, I've already talked through these breadth first and depth first search, but I go through here and I give a walkthrough where I said depth first search was basically using a stack. Well, I show the stack and I show the paths so far and I show the backups. You should go through the depth first search with loop detection, breadth first search. We've just gone through all of these, but I went through them verbally using the little diagram and pointing at things rather than trace through all of this. But you need to be able to trace through these things, because frequently on the final, I'll give you a graph and I'll say, okay, trace through this graph using depth first search, or trace through this graph using breadth first search, or trace through this graph using depth first search with loop detection. So you need to be able to trace through them and do that. Or I might ask questions like, what path would be detected with depth first search, right? And if I said that, well, your answer would be for this graph, A, B, F, A, B, F forever, right? So it fails to find the goal. If I said depth first search with loop detection, it would return the path ACGJM. And if I said, okay, well, what happens if we have breadth first search? Which path would it find? You would say ADIL. So I might ask you to give me the path, or I might ask you to, show me the order that nodes are explored in, et cetera. You should be able to do all this. Like I said, it's standard 220, 325 type material. Okay, so what are some variations on these things that we could do? Well, one simple variation is a depth limited search. So what do I mean by that? I mean, well, this is a fairly small graph, but let's say it was big. And again, you don't know the shape of this search space to begin with. It's a blind search, so you're at A and you feel out A's children, B, C, D. Well, that's all you know. You don't know any of the stuff below here when you started out, right? They're blind searches. So one thing you might do is you might say, gee, I'm going to use depth first search, but I have no idea how much this is going to cost me. And this could end up being far beyond the resources of my computer, my memory, and the amount of time I have. So maybe I'll say, let's limit the depth of the search to no more than 4 steps. Okay. Well, in this case, let's say no more than 3 steps. Well, 3 steps, you'd still find the goal. No more than 2 steps. Okay. So with no more than 2 steps, you would never reach a goal because all of the goals are more than 2 steps away. But you don't know that to begin with, so you might say, I'm only going to go X number of steps, and I'll do a depth first search. I'll go down 3, and if I don't find it, I'll mark that node as a failure, and then I'll back up and I'll do. So basically, I'll search everything until I find a goal, or I exhaust everything to level 3. Okay. And in this case, because there is a goal that's within 3 steps from where I'm at, you'd find it. But if this guy had been further away, 3 steps wouldn't be enough. You might say, okay, Mike, I can see you doing this to save time, but it's pretty crappy, isn't it? And I'd have to say, yeah, it's very crappy because I might miss my goal because my goal might be further away than I can afford to reach. So a typical way of dealing with that, that's not a very good way of dealing with that, but sort of the first first approach you might go is iterative deepening. So in other words, I search this thing for 3 steps and I don't find the goal. And I go, well, now I'm going to go 4 steps. And I research the whole thing 4 steps and I don't find a goal. So I go, I'm going to research the whole thing 5 steps. Very crappy, right? Because you're rebuilding your search tree each time. So you end up wasting a lot of time trying to do this. But sometimes, you know, life is such that you have to make a decision and all of the possible decisions in front of you are crappy and you have to take the least bad. So if I can't afford to search the whole thing, setting a depth limit is a reasonable thing to do. And if that fails, you're kind of stuck to say, well, let me go just a little bit deeper, because maybe the goal is one more step away from, you know, what I found. And you might say, well, these are bad ideas, Mike. On their own, they're not the best ideas, but these ideas get incorporated into more complex searches, which is why I'm mentioning them. So when we talk about Minimax, Minimax is a depth-limited search, but it's got ways of dealing with the fact that it's got fixes that make it not quite as bad as it would seem. Okay. So, all right. So, are there any? Let me stop. Are there any questions at this point? So, what have I covered? I've covered classic depth first search and classic breadth first search, and we've talked about the fact that these are blind searches. They're blind because they can't see. Essentially, all they can do is feel out the next level in front of them. We've talked about their advantages and their disadvantages. The biggest, both of them share exponentially increasing search times, so you can only apply them to relatively small problems. Breadth first search not only exponentially increasing search times, it's exponentially increasing memory utilization. So it's kind of a double whammy on the bad side. And we said, well, you know, one thing you maybe could do is set a limit. Say I'm going to only search no more than 5 moves ahead. I can afford that. And so that's one of the things that you could do. Any questions about these searches? Any questions about searches? Nobody wants to ask Mike a question about the searches. So I assume that this material is just a refresh for all of you guys and girls. And because of that, I'm not going to spend a lot of time on it. But again, I will expect you to be able to understand these searches on an exam. Okay. The next thing that I want to talk about is something called a state space. Now, I've kind of given you a little bit of an idea as we went through these graphs. I said, think about a maze and think about the arrows as different paths you could take in the maze. And so, while that was informal, that kind of gave you a way of thinking about how I could use one of these searches to be able to solve a problem. But normally, if you want to solve a problem, before you start worrying about searching for an answer, you have to have some kind of a model for representing the problem. If I want to solve a problem, I've got to have some way of representing that problem as a model inside my computer. And with games and puzzles and things like that, a standard way of going about it is to have something called a state space. A state space. Now, what's a state space? Well, a state space, I'll share this. A state space is really three things that you need. It's a model of a problem or game or a puzzle, right? And the state space itself has these three things in it. It's got a way to represent the state of some system at a particular moment in time by a hopefully compact description of the important characteristics of that system. So I've got to be able to have a snapshot of the problem at a point in time. So if you were thinking about a maze, the snapshot at a moment in time would be an image of the maze and a dot that represents where you are. That is everything you need to know about the problem at some moment in time. If you're thinking about a board game like checkers or chess, or even a game like tic-tac-toe, that could just be a 3x3 grid, right? A state space would usually be an array, a two-dimensional array that represents the board with usually a character in each position of the board that represents what piece is at that location. So in checkers, right, you just need, I guess, the color and whether or not it's a king or not, right? That's really all you need. An image of the board as an array, the position of the pieces on that board, and whose turn it is. In a two-player game like checkers, you need to know whose turn it is. A state space for, like I said, a maze is, okay, what's the maze and where am I at? Okay. Now the maze example, don't get confused, because you need to be able to represent the whole maze, obviously, but really at a point in time, the dot that the character's in, remember the character isn't able to see the whole maze at once. In something like checkers or chess or tic-tac-toe, both players can see the whole space, the whole state. But we can even play around with that in their head a little bit. And if you think about playing a game, right, you can think about the moves you make as going to new states within that state space, of like moving around in it. So again, the first thing you have is some kind of representation of the system, of the game board, or of the problem at a moment in time, and a compact description of the characteristics. Now, what do we mean there? That would be like rules for determining legal moves. Is what we've got there. So you have to know what's the system, and where am I at, right? And I've just given you item 2, which is a way to determine the legal moves or the transitions between the states of the system. So we've got a model of how things are at a moment in time, and we've got a way to determine our legal next moves. There's a third thing you're going to need, and that's some kind of a test to recognize when the goal's been reached. Now that might seem too obvious to mention, but it's critical. If you don't have a way of recognizing that you've reached a goal, well, then you're not going to be able to effectively reach the goal if you can't even recognize that you've gotten to it. So there's got to be some kind of a test that says, oh, I've reached a goal state. Sometimes it's necessary to have a separate test to recognize a loss. a situation from which a goal can never be reached. In other cases, that may not be necessary, but in some cases, you have to be able to know, I've reached a goal, and you have to be able, in some cases, to recognize I've reached a dead end, and this path is not going to ever get me to a goal. Okay. So then I give an example. I say in chess, checkers, and other board games, the state would probably be represented using a 2D character array, where each array location indicates the presence or absence of a piece, using different characters or codes for individual pieces, and the rules for legal moves and a test or tests to recognize winning states are generally straightforward, right? And those kinds of things. So we've now talked about what a state space is, and why we use search to be able to move through this state space. The next thing I want to do is I want to talk about a problem called the farmer, wolf, goat, cabbage problem. It's a very simple problem. The funny thing is about it is very, very simple, but though it's exceedingly simple and has a pretty small search space, it's just complicated enough to cause you have to think about it. So what is the farmer, wolf, goat, cabbage problem? Basically, you've got a farmer, a wolf, a goat, and a cabbage, and they are on the west bank of a river, okay? And there's a little boat, but the boat can only hold 2 occupants, and one of those occupants has to be the farmer, because the farmer is needed to pilot the boat across the river. A cabbage can't pilot a boat across the river. A fox can't, or wolf can't pilot a boat across the river, and neither can a goat, okay? So you can only have, at most, 2 passengers in the boat, and one of those passengers has to be the farmer. So the farmer, the wolf, the goat, and the cabbage are on the west bank of a river, and the farmer wishes to get to the east bank of the river, where his home is. I guess his fields are on the west bank. He's trying to get home. His home is on the other bank, the east bank. And so the farmer wants to get his wolf, his goat, and his cabbage to the east bank. Now, the problem is that wolves like to eat goats, and goats like to eat cabbages. So the only way that you can prevent chaos from coming is to have the farmer there to prevent the wolf from eating the goat or the goat from eating the cabbage. So as long as the farmer is on the same side as the wolf and the goat, then the wolf can't eat the goat. The farmer won't let him. And same thing with the cabbage. As long as the goat and the cabbage are on one side of the river, the farmer has to be there too to keep the goat from eating cabbage. Right? Not too difficult. Now, how could we represent this problem as a state space? Well, I've mentioned 3 different things. I've mentioned the west bank of the river where you get started, the east bank of the river where you want everybody to end up, and I've mentioned the boat that can hold 2 people. So you might think, well, I'm going to need to represent these 3 different places in my model. And you could, but if you think about it a little further, you'll realize that the boat is really just a way of causing transitions, of moving occupants from the west bank to the east bank. And so we don't have to represent the boat as a place when we realize the boat is a conveyance for moving things simply from one bank of the river to the other. So the standard way that you represent the farmer, wolf, goat, cabbage problem is by having a 4-tuple, where you've got a little listing, a tuple of 4 items in it, where you have the bank that the farmer's on, the bank that the wolf is on, the bank that the goat is on, and the bank that the cabbage is on. So everything starts out as west, 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 west. All the participants begin on the west bank of the river. And the goal state is you want everything to be east, 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 east. The farmer, the wolf, the goat, and the cabbage to all be on the east bank of the river. So that's the goal state. The starting state is everybody's on the west. The goal state's everybody's on the east. We can also represent dead spaces, dead states. So if the farmer and the cabbage are on the east bank and the wolf and the goat are on the west bank, that is a dead state, because if this state occurs, your wolf is going to eat your goat and the game is over, because there'll be no way of getting all 4 of them unless you count the goat being in the wolf's belly, and we don't. There's not going to be any way to complete the problem if you ever end up in this state, because again, the wolf eats the goat. And similarly, if the farmer and the cabbage are on the west bank and the wolf and the goat are on the east bank, the same thing happens. The wolf eats the goat. So if the wolf and the goat are alone on one side of the river, the wolf will eat the goat. If the farmer and the wolf are on one side and the goat and the cabbage are on the other side, same problem or similar problem, the goat will eat the cabbage and you will never be able to complete the problem. And it doesn't matter if whether the farmer and the wolf are on the east bank and the goat and the cabbage are on the west bank, or the farmer and the wolf are on the west bank and the goat and the cabbage are on the east bank. In either case, if the goat is left alone with the cabbage without the farmer being there, the goat will eat the cabbage. And if the farmer gets tired of this problem and simply takes the boat home, leaving his wolf and goat and cabbage, there will be a massacre that will take place as the goat attempts to eat the cabbage while the wolf is attempting to eat the goat. So those 2 clearly are dead states as well. So we've got one start state. Everybody starts out on the west bank. We've got a goal. We want everybody on the east bank. We've found out our dead states. And although it's not presented here, there's a constraint that you can move at most 2 things from one bank to the other bank in a move. And that's because the boat can only hold 2 people or two items. So what are the kinds of things that you can do? Well, really, there are only 4 things that you can do. You can have the farmer cross the river by himself. That's a thing you could do. Now, that does generate 2 rules, right? If the farmer's on the west bank, he can move to the east bank. And if the farmer's on the east bank, he can move to the west bank. I keep saying he. Could be she. We have female farmers. Notice that the location of the wolf, the location of the goat, and the location of the cabbage do not change when the farmer moves himself or herself across the river by boat. Okay? So that's one thing you can do. The farmer can move across the river by himself or herself. Another thing that the farmer can do is the farmer and the wolf can cross the river together. So the farmer and the wolf, if they were on the west bank, they can move to the east bank. That doesn't affect the location of the goat or the cabbage. Similarly, if the farmer and the wolf are on the east bank, they can move to the west bank. That doesn't affect the location of the goat or the location of the cabbage. Third thing can happen, the farmer can take the goat across the river. So if the farmer and the goat are on the west bank, the farmer and the goat can move to the east bank and vice versa. Those things don't change the location of the wolf or the cabbage. And finally, the farmer and the cabbage can cross the river together. So if the farmer and the cabbage are on the west bank, the farmer and the cabbage can move to the east bank and vice versa. These are the only 4 things that can happen, and they are represented by 8 rules because you can be going from east to west or from west to east. And that's pretty much the entire problem. So you might say, oh, this thing ought to be ought to be trivial to solve, right? So what could we do? Well, if you look at the first move here from the initial state, there are 4 moves that you could make, right? The farmer and the wolf, that was rule 3, could move to the east bank, leaving the goat and the cabbage on the west bank, but then the goat eats the cabbage. Or the farmer could go by himself to the east bank, but then the goat would eat the cabbage and the wolf would try to eat the goat. The farmer and the cabbage could cross to the east bank, but then the left behind wolf would eat the left behind goat. The only move that you could do of the 4 moves is for the farmer to move from the west bank to the east bank along with the goat. And why can you do that? Why can the farmer and the goat move? Well, because wolves don't eat cabbages. So the wolf is a carnivore. It's not a vegetarian. It's not an omnivore either. So it's going to leave the cabbage alone. So you can make that move. Okay. So at this point, I've got the farmer and the goat on the east side. You might say, well, that's good. So the next move, there's only 1 move you could make. Well, there's 2 moves you can make. One is the farmer and the goat could move back to the west bank together, but then you've moved back to your starting state, so you didn't make any progress. So yes, you get the farmer and the goat in the boat and go to the east bank, and then they could go back to the west bank, but you didn't do anything. The only move that moves you forward in any way is for the farmer to return to the west bank in hopes of grabbing other objects. So after this step here, you've got the farmer and the wolf and the cabbage on the west bank, and you've got the goat on the east bank. So what can we do next? Well, either the farmer and the wolf could move across, right? Or the farmer and the cabbage could move across. And at this point, you have either the farmer, the wolf, and the goat on the east bank with the cabbage left behind, or the farmer, the goat, and the cabbage on the east bank with the wolf left behind. And at this point, people go, what do I do next? And the reason why people groan and go, what do I do next, is any move you make seems to make the problem worse at this point. We have reached a local maxima or a local minima, depending on how you're talking about reaching your goal or minimizing costs. We're close to our goal. We're 3/4 of the way there, so it appears, because 3 of our 4 objects are where we want them to be. But any move, we're gonna start moving away from the direction that we wanted to go. And humans don't like to do that. If they feel like they're intrinsically getting closer to a goal, well, then they don't want to start moving away from the goal, right? And it's not just humans that do this. They're interesting experiments that you can do with dogs that they've done, which is you've got a dog. You've got a fence, and you've got a dog on one side, and you're trying to get the dog to go to the other, and like you throw a ball across the fence, and the dog wants to get to it, and so the dog runs up the fence and will run back and forth, right? Well, if there's a gate, the dog will if the gate's close enough, the dog will run around through the open gate and grab the ball and come back. But the further away you put the gate, the harder it becomes for the dog to move towards that gate, because the dog temptation is, right, that you don't want to get away from. I want to get to the ball. I don't want to go away from the ball. So that's an example there. And humans do exactly the same thing. Humans get stuck in these local maxima. you don't believe that humans get stuck in these local maxima, talk to someone who's in their late 20s or early 30s who are in a long-term relationship where they're unhappy. And then, you know, you have the friend conversation of, well, you know, have you thought about, you know, maybe, going your separate ways? Oh man, you know, I'm kind of comfortable but I'm miserable. But see, because what frequently happens is that, you know, you're not happy where you're at, but looking around, everything looks worse. It's like, yeah, you know, it's kind of a pain living with him or her, but, you know, if I move out, then I got, you know, to get a new apartment, and I'm going to have higher rent, and, you know, and well, you know, it's not so bad. And so humans do these kinds of things. It's really kind of funny when you take an AI course and you start studying these algorithms and you look back and you say, humans do stuff very similar to this. Okay. So let's look a little further here. Actually, let me read some of the comments here. Somebody goes, "Oh, okay, I've figured it out." Well, I'm glad, Devin, that you were able to figure it out. That's what we're working towards. Kind of like not wanting to start over on a program that isn't working. I agree with that. I gave you guys a chance to ask questions about the program assignment. My dog probably would have just smacked in the fence. Some of them actually do that. It's really kind of interesting. Humans are just computers, aren't they? Actually, I might argue that they're worse. You want to know why bureaucracy sucks so bad? Like you're trying to get something done in a bureaucracy, like tax bureaucracy or government bureaucracy. The problem is the bureaucracy is just a program that's running. And, you know, the rules are written in DMV, exactly. The rules are written in little books. And the humans, the mistake you make is when you're talking to the person, you think that, oh, I'm talking to a person. You're talking to an interface to a program. And it's a program that runs on a distributed compute system where all of the little humans are compute nodes, and they don't do a very good job because humans forget things. They have a terrible memory. They make mistakes, right? They frequently don't know all of the steps in the rule book. And that ends up with problems where, you know, one person will send you to one department for something and that person will send you to another department. Why is that happening? It's because you're asking a question of the person and they don't really know the answer, so they bounce you to somebody else in hopes that that person knows the answer. So, pretty bad. Anyway, so that's Mike's take on bureaucracies. Don't get frustrated with the people. They're just little compute nodes in an algorithm, and you have to figure your way around the algorithm to be able to get what you want. Okay, enough of that. Let's go back to our little diagram here. Okay, so what do we do? Well, we are going to have to move further away from our goal. And it can't just be that the farmer moves from the East Bank to the West Bank, because if the farmer moves by himself or herself, then if you had gone this way where there's the wolf and the goat, the wolf will eat the goat. And if you had gone this way, the goat will eat the cabbage. So the only winning move, well, it's not even a winning move, the only move that will give you any progress that you can make is for the farmer and the goat to move to the West Bank. So the farmer and the goat have to move back. In either scenario, the farmer and the goat have to move back. And humans really don't like doing that, because you're going from a state where 3/4 of your objects were where you wanted them back to a state where only one object is where you wanted it. And wasn't that where we were 2 steps ago? Right now, yeah, we swapped out the object, but we're back to a situation where it's either the wolf by himself on the east bank or the cabbage by itself on the east bank. Okay, so but now the farmer can come with the cabbage, or the farmer can come with the wolf. Either way gets us to this state where we're now at a state where it's the farmer, the wolf, and the cabbage that are on the proper side. And so now the farmer can return safely to the west bank by himself because the wolf is not going to eat the cabbage. So the wolf and the cabbage are okay. The goat is okay. Now the farmer can take the goat across, and when he does that or she does that, we reach our goal state. Keep losing my ability to scroll here. Okay. And that reaches us to the goal where everybody's happy. Now you can still screw things up if the farmer decides to actually West Bank, but I wouldn't do that. The interesting thing here is that this diagram that I've shown has all 16 possible positions mapped out. We've got a 4-tuple, right? And each entry in there can be either east or west, 0 or 1, right? So how many states can you make out of a 4-bit number? Because let's face it, that's really what this is, right? 0, 1, 0, 0, right? 1, 1, 0, 0, etc. And so this is, if you count them up, are all 16 states and all of the possible movements between those 16 states. So it's actually kind of interesting that in a problem that's so small, it'll fit on one page. The entire search space will fit on one page. Humans still don't immediately see the way to the goal. And it's basically because you reach a local maxima, right, where you feel like you're 3/4 of the way there, and the next step has to be, if you want to succeed eventually, is to move from a state where you look like you're 3/4 of the way there back to a state where it only looks like you're 1/4 of the way there. And it's very hard for humans to do that. Now, if you sit down and work it out like this, you go, oh, it's obvious. And if you think about it, it all makes sense. But again, there are only 2 paths through the state space, right, from the initial start to the goal, and it requires that you get past this local maxima if you ever want to reach your goal. So that's a state space. You could solve the problem. This is small enough. You could solve it with either depth first or breadth first search, right? And this is a kind of example of the sort of problems that in the early days of AI you might attack with a weak general method like state space representation and search. Questions about this? Questions? Are there any questions about this? So what have we done right now? We've described what a state space is, right? It's a way of a compact representation of a problem state, some way of knowing the legal moves, and some way of recognizing you've reached a goal, and in some instances also some way of recognizing that you've reached a loss, a dead state. And that's really what a state space is. If you can take a problem and map it to a state space representation, then you can use a search technique to be able to try possibilities. And that's enough to solve a wide variety of very simple problems. Or I shouldn't say very simple, I should say very small problems. But what happens if we want to solve a larger problem? Well, we've got to find a way of um, of overcoming the limitations of our searches. And you can probably see where we're going to go here because I referred to depth first and breadth first search as blind searches. So if they're blind searches, can't we add something to our site or to our search that gives it the ability to see, right? To be able to have some way of seeing into the future. Now, if we had perfect sight, if we had perfect knowledge, then you wouldn't need search. Why not? Because if you had perfect sight, perfect knowledge, you could just walk straight to your goal. I mean, it's not much of a maze problem if the maze has a path that is a straight line from the entrance to the exit, and you can see the exit. That's called a hallway, right? So if you have perfect sight, if you can see your goal from where you start at, there's not much of a problem there. But we're interested in problems that are more difficult, but that are too difficult to just throw depth first search at or breadth first search at. So what can we do for that? Well, the first thing we do is we introduce the concept of something called a heuristic. A heuristic. A heuristic is a rule of thumb. That's the way it's often described. And basically, it's an estimate. That's what a heuristic is. It's a way of estimating. And what are you estimating? Well, generally, you're estimating either the cost of something or the distance. So if I'm representing like the cost, I'm trying to minimize the cost. If I'm representing distance, I'm frequently trying to minimize that distance to move closer to my goal. So that's what a heuristic is. It's an estimate. It's some knowledge that allows you to make a guess. Okay. In my notes, I define a heuristic as a quick and inexpensive way to estimate the value or cost of something. And there are lots of real life heuristics. Bright red apples are tasty. Is that guaranteed to be true? Of course not. That bright red apple might be made of wax, okay? Or maybe that bright red apple that looks so nice and shiny has a worm in the middle of it. Could, you don't know, all right? Might be rotten at its core. It only takes one bad apple, you know? But in general, if an apple is bright and red and shiny, then we think it's going to be tasty. And if you don't believe me, walk into Super One or wherever and look at the apples. They're all nice and bright and red and generally polished, so they're shiny, because that's what people want. They don't want the apple that's all dinged up and's got a bruise spot on it, even though that one might be more tasty. We often use price as an indicator of quality. A terrible heuristic, right, that businesses often gouge us on. But in general, people believe that better things are more expensive than things of lower price. Is that true? Sometimes it's true. It's not always true. It's frequently not true, but people often use that. A heuristic from a game might be in checkers. You might say, well, if I've captured more pieces from my opponent than my opponent has captured from me, the difference between those piece counts is a good indicator of how close I am to winning or losing the game. And in general, that's not a bad heuristic. Why are heuristics important? Because you're adding some knowledge to the search. You're allowing it to see a little bit into the future. And we can use that to to sometimes improve our searches. Now, some heuristics are what we call admissible, and other heuristics are what is called inadmissible. An admissible heuristic is a heuristic that never overestimates the cost of reaching a goal. An admissible heuristic is an optimistic heuristic, okay? It's not pessimistic. An admissible heuristic is either going to be right on the money, or if there's any error in it, it's going to think that you're closer to the goal than you actually are. It's optimistic. It's like, we're almost there, or it's just around the corner. So that's admissible, right? An inadmissible heuristic is one that's going, oh, we're so far away from, that overestimates the cost. So inadmissibles, they're kind of the boring, depressing heuristics. Admissibles are either accurate, or if they're inaccurate, they err on being overly optimistic, on thinking that you're closer to the goal than you actually are. Admissible heuristics are important because there are some algorithms, we're going to talk about one called A star, that if you give it a admissible heuristic, the algorithm will be able to guarantee you that it finds the best solution. If you give it an inadmissible heuristic, that's not always the case. Now, this doesn't apply to all algorithms, whether the admissibility or inadmissibility of the heuristic matters. And specifically, it doesn't on the first algorithm that we're going to look at, which is called hill climbing. Hill climbing is the most simple, probably the most simple heuristic search. So we're now talking about heuristic searches rather than blind searches. And pretty much the simplest heuristic search is called hill climbing. Before I go through the steps here of it, why don't I just give you an understanding of it by just describing it in general English. Hill climbing, we imagine our world as a three-dimensional world of crests and valleys, and we want to reach the top of the highest hill or the top of the highest mountain. That's our goal, to get as high as possible. That's the goal of hill climbing, is to get as high as possible. So what does hill climbing do? Well, hill climbing uses a heuristic that basically says, I'm at this position here, and I'm going to use my heuristic to look at all of the positions around me. If one of those positions around me is better, is higher than I am currently, I will move to it. And then I will simply repeat the process. Okay? So that's what hill climbing will do. Now, you can think about it as, from a human point of view, unless your heuristic is just really, really good, it's like you're standing in an open space that's very, very foggy. The worse your heuristic, the thicker the fog. The better your heuristic, the lighter the fog. So with a better heuristic, I can see further. With a poorer heuristic, I cannot see as far. So the fog is basically how good is the heuristic. It's very foggy, you got a terrible heuristic. If the fog is so thick that you can't see at all, you're basically back to a blind search. So you're standing there in the fog, and you want to reach the top of the mountain, or the top of the hill, the highest hill, and you suffer from amnesia. So you don't remember anything about where you've been. You do know where you want to go. You want to get to the top of the hill. And so you look around as best you can through the fog, and if you see a spot that's higher than the spot that you're currently on, you move to that higher spot. And that's the whole algorithm right there. Now, clearly, hill climbing suffers from a potential problem, local maxima, right? I've reached the top of a little mole, and I look around, and every step takes me further away, further down, right? And so I just stop there, and I'm stuck. It's like the guy or the girl in the unhappy relationship. They're stuck. Every step looks way worse than where they're at right now, and so they know that they're not where they want to be, but they can't move. That's hill climbing. Okay, so let's look at it algorithmically. Let the current node be the initial problem state. If the current node is a goal, then you return. I mean, if you look down and you go, oh, I'm at the highest point, well, that's great. You won by doing nothing. Otherwise, if you're not at your goal, initialize H prime to be an arbitrarily high value if we wish to minimize the cost of H, or arbitrarily low value if we wish to maximize H. In other words, I will set my current position when I start to as horrible as possible, okay? So if I'm trying to minimize, as horrible as possible is a very, very high value. If I'm trying to maximize, as horrible as possible is a very, very low value. But anyway, I'm going to make myself move off the spot that I'm on, unless, of course, we did this check at first and we found out that we were at a goal, so we returned before we got here. So assuming you're not at a goal, make the current position miserable, okay? And then go into a loop that will repeat. Examine the children of the current node, computing the heuristic function for each child. If there exists a child node with a better heuristic value than the current value, which there will be for the first step because you've made your current position miserable, then select the child with the best heuristic value as the new current node. Otherwise, set the no better child flag, which means I don't know what to do because every step I could take would be worse than where I'm at. You repeat this loop until either the current node is the goal or the no better child flag has been set. So you will repeat taking steps until either you find a goal or you every step would take you away from the goal. That's all of hill climbing. And no better depends on whether you're maximizing or you're minimizing. So what's the advantages of hill climbing? It does use knowledge about the problem, so it isn't blind. And you could say that another advantage is that it's really simple to implement, right? The disadvantages, it's not guaranteed to find a solution, much less an optimal solution. It often gets stuck at local maxima. And if we think about our farmer-wolf goat problem, farmer-wolf goat cabbage problem, hill climbing would not work because, like we said, we reached that local maxima where 3/4 of our objects are where we want them to be, and every move looks like it takes us further away from our goal, and hill climbing just freezes up and says, I don't know what to do. Now, there are some things you can do if you get stuck with hill climbing. Is you can just say, oh, I'm stuck, move in a random direction. Or sometimes I'm stuck, move in a random direction, X number of steps. In other words, I'm stuck, I'm not where I want to be, and I have no idea what to do, so just strike out in a random direction. Some people do that in relationships. They're miserable and they get in their car one day and they just don't come back. So that's the hill climbing solution where you just say, I'm going to move in a random direction, some random number of steps to get me away from here, and then I'm going to start trying to maximize again. Maybe that'll help. Okay, so here is a graph. This is exactly the same graph that we had before, only now I've added heuristics to nodes. Now, to begin with, you don't know what all these heuristic values are when you get started. You start out at A, and in this case, I'm trying to minimize, so I set my H value to be infinity, right? So that'll make me move off of A. A looks at its children, B, C, and D, calculates the heuristic, which says, okay, how close do you think you are to your goal here? Well, I think if I move to B, then I'm 1 step from my goal. If I move to C, I think I'm 3 steps to my goal. If I move to D, I think I'm 5 steps to my goal. So I will obviously move to B, okay? And then B, I look at its children, and B says, well, if I move to E, that's infinite, and if I move to F, that's 10. But I think I'm only 1 step away, but any step I take takes me further away. I'm just going to sit here and pout. And so hill climbing would go from A to B and get stuck, right? Now, let's say, though, that we change this. Instead of saying 1 here, let's make that 10. Okay, so in your mind, just change that to 10. And in fact, because this is word, I can do that. So now what would happen? Well, I'm at A, and I look, and if I go to B, I think I'm 10 steps away. If I go to C, I think I'm 3 steps away. If I go to D, I think I'm 5 steps away. Okay, who are you going to go to? C, of course, because I think C is the best one. It's the closest to my goal. It's the lowest cost, highest altitude, however you want to think about it. Again, we're minimizing in this particular situation here. C has 2 children, D and G. D thinks it's 5 steps away from the goal, applying its heuristic function. G thinks it's 2 steps away from the goal, applying its heuristic function. So what are you going to do? You're going to go to G. G only has 1 child. There's only 1 step you can take from G. That's to go to J, and G thinks it's 2 steps away. J thinks it's 1 step away. Oh, well, I'll take a step, and that'll take me to J, and I think I'm 1 step from the goal. J has 1 child, and it's the goal. So it's not just an H prime of 0. Actually, you know it's a goal, so the cost is actually 0 here. The prime is usually used to indicate this is an estimate, right? And so frequently when you write a heuristic, you'll go H prime to mean this is a guess. This is an estimate of a number. I don't know the real value. But anyway, in this case, hill climbing would work. It would get you from A to C to G to J to M. It found a goal in this case. It didn't find the shortest path. Why didn't it find the shortest path? Well, because this heuristic here was actually overly negative. It said, oh, D is 5 steps away from the goal, when actually it was only 2. And I thinks it's 3 steps away from the goal, when it's actually only 1. So this is an example of a non-admissible heuristic because it's overestimating cost. It's leaning not towards optimism, but it's leaning towards pessimism. Okay. Let's see, in here, I go through what I just went through above. So that's just walking through it as I verbally went through it. Okay. Now, let's say that you had perfect knowledge. Okay. Let's say you had perfect knowledge. So this is the case where your heuristic is so good that it gives you perfect sight, so there's no fog at all. Because there's no fog, it knows accurately how far away things are. The heuristic is just that good. So in this case, because you've got a heuristic with perfect knowledge, you're at A, it's terrible. You set it to be purposely terrible. You look at B, B is the dead end, essentially. It's infinite cost, which is true because E is cost infinite because it's a dead end, and F is a loop, so it's infinite. So going to B costs infinitely. I'm just showing you here that I set these values accurately. B really is infinitely far away from the goal. If you go to B, there's no way you can reach a goal from it. If I look at C and I look at D, C thinks it's 3 steps away from the goal, D thinks it's 2 steps away from the goal. And in fact, if you look, C is 3 steps, 1, 2, 3. And G is 2 steps, and J is 1 step, and M is no steps, right? And you look here, these are all correct. This I is 1 step away from the goal, D is 2 steps away from the goal. So if you're using hill climbing here from A, the best guy is D. It's the one with minimum cost. It's the closest. From D, you choose, am I going to choose infinity or am I going to choose I? Well, clearly you choose I. And from I, you could go infinite cost, or you could go to one that is the goal and you take it. So with perfect sight, with perfect knowledge, hill climbing gets you to the goal because essentially there is no search. You can see where the goal is and you just walk to it. At each step, you know exactly how far away you are from the goal. So you you go directly to the shortest, closest goal. Does that make sense? Does that make sense? Okay. So again, hill climbing, if you have perfect knowledge, it'll go right to a goal. In general, even with an immiscible search, hill climbing is not guaranteed to find the best path or even a path because it can get stuck. And if you don't believe me, if we change C value to H of 1, so if we made this a 1 here, come on. If we made this a 1, it's still an admissible search. It's no longer got perfect knowledge. It's still an admissible search because it's overly optimistic, okay? It thinks C is only 1 step away, but it's actually, all right, 3 steps away. Hill climbing would move to C and get stuck because it thinks it's only 1 step away from the goal. If it goes to G or D, it'll think it's 2 steps away from the goal. So hill climbing, even with an admissible search, is not guaranteed to find a solution path. So hill climbing is a terrible algorithm, but it's sort of the very first one that you would think of. Are there better algorithms that use heuristic search? And the answer is, of course there are. And if we look, what we're going to be covering next time is we're going to be talking about A-star and Minimax. A-star is what's called a best first search algorithm for graphs. A-star is pretty much the standard algorithm that's used for single player games, like searching a maze. And Minimax is pretty much the standard algorithm that's used for 2-player games. I say the standard algorithm, Minimax still is, although there's a new kid on the block called Monte Carlo search trees, and those are similar to Minimax, but are better. A-star is going to use a function that contains 2 pieces of information. it contains a G function and an H prime function. The G function for some node N will keep up with the true cost of reaching node N. How much did you spend or will you need to spend to get to node N? How many steps will it take you to get to node N? Plus an estimate of how many steps do you think it'll take you to get to the goal from N. So G is the actual cost to reach node N. H prime is the estimate of how much more will it take to get to the goal from step N. Now notice G doesn't have a little prime on it, right? And the reason is you know the actual cost, if you're doing a search, of how many steps you had to take to get to node N. So this isn't an estimate, it's a computable value. H prime is a heuristic, it's an estimate. So this is the guess part, this is a actual cost part, but if you put them together, they give you F prime, it's an estimate, right, of the total cost of reaching a goal through node N. So that's what A star does. A star says, I'm going to consider both the cost it took me to get to a node and my best guess of how much more it will cost to reach the goal from this node. And if I put those together, it gives me an estimate of the total cost of reaching the goal through node N. And by doing that, I can build a search that always takes the best option first. That's why A star is called a best first search. And if we look, we're going to talk about it in detail next time, but I ended up with a couple of minutes. So our old standby graph here, it's the same graph, but now instead of just having a heuristic function, I have a cost. And in this case, each little arrow costs me 1. So if my estimated cost of reaching the goal from node B is 1, my F prime is going to be 2 because it's the 1 from the heuristic plus the 1 that you already spent to get to B. So I think my total cost of getting to the goal through B is going to be 2. I think from C, I'm going to need 3 steps to get to the goal. I think from D, I'm going to need 5 steps to get to the goal. But since it cost me a step to get to D, the total cost through D is 6, and the total cost through C is 4. And basically what you do is you start out, you open your children, and you say, okay, which one looks best? Well, B looks best because it's got a total cost of 2. So, okay, now I'm going to go A to B, and I look at its children. Well, the picture isn't nearly as rosy when I look here. I think it's going to cost me 12. And I think it's going to cost me infinity here. So right now I've got E, F, C, and D. Infinity, 12, 4, and 6. So I went from A to B, but then I'm going to put that path on the back burner for a while because now it looks like actually if I go A to C, I'll be in better shape, right? And now from C, I look and C has G and D. Well, G thinks it's going to be 2 steps, but I will have expended 2 steps to get to G. D thinks it's 5 steps. I will have expended, well, 2 steps, 5 plus 2 would be 7, but I already had opened up D earlier and it had a smaller cost. Oops. So I'll just stick with that smaller cost. But anyway, you can see, and then I'm going to go to G because I think it's cost me 4. So that'll give me J. And J, I still think it's going to cost me 4. You notice what's happening here. I'm going, oh, total cost is 4 through C, total cost is 4 through G, total cost is 4 through J. And I don't have any other guy opened that looks better right now. So while that's the case, I keep plotting through. And A star would give me A, C, G, J, M. You might have said, well, but that wasn't the best path. Why not? Because this guy had an inadmissible search. It overestimated the cost of getting to L from D. It said, oh, it's going to take me 5, I think. But really, it would have only cost you 2. So it caused me, because this search was inadmissible, it caused me to overlook D because it looked like I always had a better path going through this path here. So we're going to pick it up here next time. We're going to talk about A-star in more detail. We're going to talk about Minimax in more detail. But these heuristic searches are searches that try to control how much searching you need to do by using heuristics that add knowledge to the system. And we'll talk a little bit about how that's being tweaked these days to take these ideas and merge them with machine learning and things like Monte Carlo search trees, where we're trying to get away from humans hand coding things like the heuristics and humans hand coding the rules, and instead letting the systems discover these on their own through reinforcement learning. So these old ideas are still used and still very useful. It's just that we're trying to take what used to be the human putting the knowledge in the system and trying to replace that with the system learning these things on its own. Okay, so that's it for today. I'm going to stop the recording at this point. I will stick around in case you have any questions. I'd be happy to answer them. But otherwise, have a good day. I will see you guys on Thursday. Remember, your programming assignments are due at 9 a.m. on Thursday. Take care. Bye-bye.